and live. Okay, so as I said before, there are other types of rectified linear units, but this is the most effective one for classifying or helping to classify or activating, I should say, the CNN. Okay. Now, ReLU activation. This is essentially what we're trying to do from increasing nonlinearity. Is we're trying to get rid of these dark values. This is just the input image, black and white, just to kind of keep it simple. But of course, we have different images with different colors and so forth. All shadows disappear from light to dark in a linear progression. So this is the image here, and if we apply ReLU to it, this is the same image right here. This image right here is this right here, and then input. This is the input feature map. Applied rectified feature map to it. Okay, gets rid of the black areas as we see here. You can see like there's a black line here. It's kind of hard to see, but if you zoom in. It's that black line right there, linear black, some black here, black, black, black. When we apply ReLU to it, look here, nothing, right? There are black areas, but there's varying degrees of it. That's what we're trying to do. By increasing nonlinearity, we're increasing that threshold value from white to dark, white to dark, white to dark, and that helps us to derive information from the image. Okay. If you want to know more about this, because we can take forever to really talk about this, but go to this website right here, get this paper. Read through it, and it'll go in more detail and probably into more of the mathematics that goes into ReLU activation of the ReLU feature, rectified linear units. Okay. So now, with what we call the max pooling layer, what we're trying to do is we're trying to want to be able to recognize images of all shapes and sizes and different angles. And so forth. And what we try to do is we try to do the max pooling layer. This really tries to kind of concentrate everything into one. The pooling layer essentially reduces the number of parameters in the image that are too large, and it also increases a very important thing called spatial invariance. We'll talk a little bit about that in a minute. And that's a very important thing, but there are different types of pooling. There's what they call average pooling, sum pooling. Max pooling takes the largest element from the feature map and kind of concentrates everything down into one. But what we're trying to do is we're trying to detect the features within objects, even though they may not be exactly how you see them. So this makes the pooling layer makes the CNN more flexible. Now with spatial invariance, sometimes images are, as I said right here, like upside down or sideways or on its side. If you look at a bicycle, for example, we've learned through things, probably seeing thousands and thousands of images of bikes by now. We can detect, we can classify it by no matter what angle we see it at, whether it's on the ground, whether it's on the side, whether we're looking at it from the back, or from on top, or from the front. We know that because our spatial invariance in our brain, we've increased it over the years. We can tell that a bike is a bike, no matter what angle we're looking at from. And just like here in the pooling layer, you see this cute little puppy dog here. It's tilting its head towards the left or right, I guess you could say, and then the other way around here, and then it's kind of in a stretched side here. No matter what, we can tell it's the same dog. Is that right? Because of our spatial invariance. Okay, and this is what the max pooling layer, the pooling layer, is trying to do. That's one of the most important features. It's very important to realize that, because that really makes the our CNN flexible. And actually, there are other forms of CNN now. I probably mentioned this in the first part here. They're like harmonic CNNs and what they call SCAT-nets now, which use a scatter type of algorithm to extract more information from the convolutional neural network, convolutional layer, I should say, or sorry, the convolutional layer rather. But like I said, we're just covering the kind of the basic things we call with CNNs and so forth. Now, when it comes to, we already covered spatial invariance. So when it comes to the flattening layer, what we're trying to do here with this is we're trying to just take all the most important features of what we covered in the convolutional layer and the pooling layer, and now we have just one kind of vector of the most important features of of the CNN, and this is what we use to then utilize classification. This, even though this is the last layer of the CNN, this is actually the first layer of our ANN, which is going to go into the ANN to help classify. And all this does is takes the pooled featured map and flattens them into one vector column numbers. Let's say right here, okay. And this is just another example. Okay, just takes them in and just takes the most concentrated ones here. So really, this is this just in one vector. This is a matrix. This is a vector. So what we do with the ANN, or the fully connected layer, the reason why we call it fully connected as opposed to a regular ANN is that they have some hidden nodes that don't have to be fully connected to each other. In a CNN, the ANN does have to be fully connected. So here's our flattening layer that we saw a couple slides ago, right here. This is it over here. Sorry, this is it over here. This is kind of the tail end of the convolutional layer that will be the input of our fully connected ANN. So as I mentioned before, the CNN can't classify its images directly. It needs an ANN to do that. So the weights, just like a regular ANN, gets adjusted through backpropagation and through bias, which are the parameters. It reduces the cost function on the end of this, and through backpropagation, it'll backpropagate through the net and to readjust the weights and values to reduce that cost error function to its absolute minimum. The layer will flatten it into, like I said, a single layer and feed it into the fully connected neural network, like this one here. So the feature map is converted into a vector. And then we use a softmax function to do to help do our classification at the end right here. So I'm going to talk about. So when it comes to our softmax function, this has to do with helping us to classify the image into what we want to classify it as. So, for example, this right here, this is a softmax layer, they call it, or a softmax function. This class 1, class 2, class 3. These are just generic types of names. This could be a bus, this could be a car, this could be a human, this could be a butterfly. Who knows what it is? And depending on how strong the connection is to the last layer, these last hidden layers, this neuron output layer in the softmax will listen to these neurons more. So it looks like all these neurons here are kind of pinging these two and kind of leaving these alone. So it's probably not going to really bother with these. So these have the strongest connections. So therefore, class 1 and class 2 are going to be activated the most. Is that right? And so the neuron, like I said, the neuron with the highest value, highest value rate gets the most attention. All right. So these two are getting the most attention here. The output node learn which nodes to listen to, just like in a regular. And here we go with a regular softmax function. These use in multiple classification logistic regression models. They use 1 and 0 values go into P, and the values on the left go into Q. This is the equation, by the way. Okay, the softmax function equation. So these Q values are where the percentage values of either dog or cat go into Q, and the P values from 1. This is the classification: 1 if it's a dog, 0 if it's not. Go into here. So now the classification error is used to measure the performance of other types of functions. Mean squared error is another one. We use cross entropy. This helps us access the network and get it to the optimal state better than for classification, not something like regression. Okay, so as we can see, we have like this example here. We have 2 neural networks, 1 and neural network 2. And what we're seeing here is that between these neural networks, which are both getting it right, but the thing is that this one here has a 90% accuracy rate, that it believes that this picture here is a dog, so it labels it as 1. It believes in a 90% probability that it's right, and only believes that a 10% probability that this is a cat, which is why it labels it 0. Okay, the neural network, it's also right. It's a but this is less though. It's not as correct. It's 60% versus 40%, and cat right here, same thing. I believe 90% probability that it's a cat, so it labels this as 1, and 10% value that it's a dog, so it labels this as 0.